Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a pretty fascinating and, dare I say, controversial topic. Can vision language models actually complete video games? We're talking about a recent surge in research showing these models not just recognizing objects or following basic commands, but actually strategizing and winning complex games.
Yeah, I saw that paper. Pretty wild, right? I mean, for years we've been saying that deep learning is good at pattern recognition, but this feels like something more. Like they're actually starting to understand the rules of the game, the dynamics, the whole shebang.
I'm a little more skeptical. I think complete is a very loaded term here. Are they really understanding the strategy, or are they just exceptionally good at pattern matching and conditional action selection based on vast data sets?
That's the million-dollar question, isn't it? My gut feeling is that it's a bit of both. There's definitely a brute force element, just throwing tons of data at the problem until it spits out a solution. But there also seems to be something emergent happening, a kind of implicit understanding of the game world.
Right, and that's what I find so compelling. It's that emergent aspect. Thinking about it from a neuroscience perspective, it's almost like we're seeing simplified versions of neural circuits learning to navigate complex environments. Not exactly the same, obviously, but maybe it gives us a clue about how the brain handles similar tasks.
Exactly. The complexity of these video games is a real test. You've got interaction, you've got physics, you've got evolving situations. If a deep learning model can successfully simulate all that inside a video game engine, that suggests a much deeper understanding than just memorizing image patterns.
But what kind of understanding? Is it the same kind of understanding a human player has? I doubt it. We have an intuitive sense of physics, strategy, and even the intent of the game designers. These models are probably just exploiting statistical correlations. Think about it, they're trained on massive data sets of gameplay, so they're essentially learning to mimic successful strategies without any real comprehension.
I agree with that to a point, but there has to be some level of internal representation of the game world for these models to function. They're not just looking at pixels and randomly pressing buttons. They're tracking objects, predicting trajectories, and planning actions. That suggests an underlying coordinate system and an ability to translate between different representations, like the visual input and the internal model.
And that translation piece is huge. It connects to my own thinking on this. How do we get these models to really understand context? I mean, they can do impressive things, but they still lack a deep awareness of their own internal states, their limitations, and the broader implications of their actions. Giving them a more neuroscientifically informed architecture, one that reflects how the brain processes information, might be the key to unlocking that deeper level of understanding.
Yes, and if they do have this internal representation of the game world, that's a massive leap forward in getting to AGI, right? Because that means they're not just reacting to stimuli, they're actually building a model of their environment and using that model to reason and predict. Think about the implications. Robots navigating real-world environments, AI systems making complex decisions in dynamic situations. This is the stuff of science fiction becoming reality.
Wow, hold on a second. Let's not get ahead of ourselves. AGI is still a long way off, and I think this focus on deep learning and neural networks is actually hindering progress. We need to incorporate symbolic reasoning and knowledge representation into these systems. We need neuro-symbolic approaches that can combine the strengths of both paradigms. Otherwise, we're just building incredibly sophisticated pattern matchers that are ultimately brittle and lack true generalizability.
I agree that current deep learning is probably a bit too brute force, but I don't think it's a dead end. I think we need to figure out how to inject more structure and logic into these models. We need to understand how the brain represents spatiotemporal relationships and how it translates between different coordinate systems. If we can crack that nut, I think we can unlock a whole new level of intelligence in AI.
And that's where the idea of neural languages comes in, right? Standardized representation systems inspired by neuroscience that allow different AI systems to communicate and collaborate. Imagine an AI system that's really good at visual recognition working seamlessly with one that excels at logical reasoning, all because they share a common neural language for understanding the world.
That's a fantastic point. Interoperability isn't just about connecting different software platforms. It's about ensuring that different data sets representing different aspects of the world can be meaningfully combined and processed. We need a unified language for AI, much like we have unified languages for human communication.
Yes, but a neural language shouldn't be just another layer of statistical associations. It needs to incorporate symbolic representations of knowledge and reasoning. It needs to allow AI systems to explicitly represent concepts, relationships, and rules. Otherwise, we're just building a Tower of Babel where everyone is speaking different dialects of deep learning.
I think the key is translation. The neural language needs to be able to translate between different coordinate systems and different levels of abstraction. It needs to be able to take raw sensory data and convert it into a symbolic representation, and vice versa. That's how the brain works, and that's how we need to build AI systems.
Okay, so let's bring this back to the video game example. We've got vision language models that can play these games. From each of our perspectives, what's the next research direction we should be exploring?
I think we need to scale this up. Let's see if these models can handle even more complex games with more dynamic environments and more diverse player behaviors. Let's push the limits of deep learning and see where it breaks down. We also need to develop better evaluation metrics for these models. Success rate is not enough. We need to measure the quality of their gameplay, their efficiency, and their ability to generalize to new situations.
I think we need to move away from the purely data-driven approach and start incorporating symbolic reasoning into these models. Let's build AI systems that can explicitly represent the rules of the game, the goals, and the strategies. Let's explore neuro-symbolic algorithms that can combine the strengths of both deep learning and symbolic AI. Maybe even create a system that can learn the rules of a new game without needing massive amounts of training data.
I think we need to focus on the spatiotemporal aspects of the game world. How are these models representing the positions of objects, their movements, and their interactions over time? How are they translating between the pixel-based visual input and the internal coordinate system that enables actions? Let's develop algorithms that can seamlessly translate between different coordinate systems, ensuring that the core logic and reasoning remain consistent despite the shifting context.
From a neuroscience perspective, I'm fascinated by the idea of reverse engineering the neural circuits that are responsible for game playing behavior. Can we use these vision language models as a kind of virtual brain to study how the brain learns and reasons in complex environments? Can we identify neural correlates of human gaming decision making? And can we use that knowledge to build more neuro-inspired AI architectures that are more efficient, more robust, and more collaborative?
That's amazing. Imagine mapping the learning patterns of these AI systems onto actual biological systems. It could give us real insight into how our own brains work.
I'm just worried we're putting the cart before the horse. Shouldn't we have a better understanding of actual cognition before we start trying to replicate it with algorithms?
Well, isn't that the whole point of research? To learn by doing, to experiment and see what works. We might not fully understand cognition yet, but that doesn't mean we can't make progress in AI. And maybe, just maybe, by building these AI systems, we'll gain a deeper understanding of ourselves.
Exactly. It's an iterative process, right? We learn from neuroscience, we build AI, we learn from AI, and we refine our understanding of neuroscience. It's a virtuous cycle, or at least it should be. And the potential payoff is enormous: more intelligent machines, a deeper understanding of the human brain, and a more collaborative future for humanity and AI.
I'm so excited to see where this all leads. It feels like we're on the cusp of a major breakthrough.
I'll believe it when I see it. But I'm willing to be proven wrong.
Me too. The path to AGI is long and winding, but I think we're finally starting to see some glimpses of the destination.
Well, this has been a fascinating discussion. Thanks everyone for sharing your insights, and thanks to our listeners for tuning in to Cognitive Spirals. Join us next time as we delve into another intriguing topic at the intersection of neuroscience, cognition, and machine intelligence.